introducing someone from our department, one of my colleagues, since 2012. Umut Orguner completed his bachelor's, master's, and Ph.D. degrees here. He worked with Professor and he did his postdoctoral studies between 2007 and 2009. He first held his postdoctoral studies in the Division of Automatic Control at the Department of Electrical Engineering in Linköping University in Sweden, and subsequently he was an assistant professor in the same department, and since 2012 he's with us. His research interests are in estimation theory, multiple model estimation, target tracking, and information fusion. So please join me in welcoming Professor Umut Orguner.
Thank you very much. Thank you for the introduction, and thank you for this opportunity. So today I'm going to be talking about target tracking, what is it, and a very basic application, a subproblem of target tracking called data association. So the outline of my talk is going to be, first I will mention what is actually target tracking, and the difference between Bayesian state estimation and target tracking. I will try to emphasize that. And then we're going to look at the target tracking under clutter. Clutter means spurious measurements that we get from the sensor. So I will be working on a very simplified problem, and then I will consider each of these cases going in the direction of increasing difficulty. And then I will give some references after the results. So we can start with what is target tracking. So it is the name given to this research area where we are estimating some quantities. These quantities are called as states, and they are the difference between estimation theory is that these states are non-stationary. So their stochastic structure is actually changing in time. And we would like to use estimation theory in order to estimate those. The applications are various, so some of us are not really innocent. They are doing military air surveillance most of the time with radars, but there are also civilian applications. In every airport there is a tracking system established. So some more innocent applications are video surveillance systems and robotics, and probably localization problem in communications. So it is an area between control theory and signal processing. So where you publish your results changes depending on the level of mathematics that you're using. So the probability, it's basically a probabilistic area of research. So you need to know really lots of probability theory. It is still a very active and expanding research area. So when I say a tracker or target tracker, we are talking about an algorithm in the computer. But the target tracker is not really connected to the world directly. So before a target tracker, so this is a block of tracker, there is a sensor and a measurement processing unit. If you are working with the radar, someone should process the electromagnetic waves that you receive, and they need to generate you some position, some kinematic measurements at the end. Or if you are working with a video camera, then you need to have an image processor before the tracker. So this is in some way good, because if your tracker is not working, you can always blame the other guy. So you can say that the other guy is not really working. So signal processing guy didn't do his job. You can say that. But there is also the disadvantage that the result that you process is seen by the user. So you are the first guy to be blamed. The tracker is not working, they say. So even if there is a problem in the sensor or the measurement processing unit, you're going to be the first guy to be blamed on. Okay. So a tracker is composed of some blocks that are called gating association. We're going to see those today. And of course, at the core of the tracker, there is an estimation and prediction algorithm. and also you have to handle the quantities that you estimate. The quantities that you estimate are called as, the estimates that you calculate are called as tracks, and there has to be always a track handling operations in a multi-target tracker. So, as I said, at the core of every target tracker, there is a Bayesian state estimation algorithm. When we say, I will talk about what we call Bayesian, but we have mainly two equations. The x represents the state that we would like to estimate. In it, there are kinematic quantities like position, velocity, and there can be some attribute quantities like type, color, etc. So state can be composed of continuous and discrete variables, and this state is actually changing with some dynamics here. So I have this dynamic equation plus some noise. This noise here is called as process noise, and it represents our lack of knowledge about the behavior of the change of the quantity here, xk. Then we have also the measurements which are related to this state xk in some known manner. So for example, in state there can be x and y positions, and in measurement y there can be range and azimuth measurements here. Of course, not all sensors are imperfect. So therefore, we model those imperfections by adding another noise term here, Vk, which is called as the measurement noise. So we have these two equations, and our aim here is at the end to obtain the posterior distribution, posterior density of xk given all of the previous measurements. So we would like to obtain a density. So we are not just giving an estimate. An estimate is just, the target is here and its velocity is at this point. It's an estimate. Here in Bayesian estimation, our aim is different. We ask from the estimator much more, that we would like to get the posterior density, whole distribution, which is an infinite dimensional vector, actually. So therefore, when we say Bayesian here, our aim is always obtaining a form of posterior density instead of a single estimate. What does posterior density give us? It gives us an uncertainty measure. When I calculate an estimate, if I know the density, then I know how uncertain that estimate is actually. So without an uncertainty estimate, without a covariance, or without this density, the estimates are more or less useless. They give some information, but it's not complete. So here, in this, so that is the process noise and the measurement noise discussion here. And as I said, this is an infinite dimensional estimation problem, because we would like to estimate an infinite dimensional quantity here. So in general, if you have taken a probability course before, then the estimation of this posterior distribution is done in two steps. The first step is called as prediction, and the second step is called as the update, or measurement update. So we have the previous posterior distribution here, and we first update time. So we predict the future, what is going to happen in one step ahead of us. And then we add the current measurement to obtain the current posterior distribution. So in general, every Bayesian state estimation algorithm can be divided into two parts. Prediction update, propagating time, so given the previous measurements, what will be the our current prediction about the current quantity. And when we take the measurement, actually, we update that prediction to obtain the posterior distribution here. So as I said, for example, in this department, if you have taken the course 230, the basic probability course, then you can always write these recursions with this with the probability theory that you have learned. So prediction update can be actually exactly given with this type of integral result. Here is the previous posterior distribution, and here is what we call as transition density. And then we obtain the predicted distribution here after the integral. So these are coming from the base, and the second part is the measurement update is nothing but the base theorem here. You update your predicted distribution here using the so-called likelihood, and you normalize it in the denominator. So therefore, the solution to this estimation problem is known by these two recursions. But the actual problem is, how am I going to calculate an infinite dimensional quantity? How am I going to represent it in the computer, etc. So there is some terminology in this area about the densities. So this is called a predicted density. So as this distribution of xk given all of the previous measurements here, and this is called as predicted measurement density. Every Bayesian algorithm can actually predict the measurements that you are going to get in the next sampling instant from the sensor. This is a very important qualification. So it is going to be very important. Therefore, this predicted measurement density will be very important in this presentation in the forthcoming parts. So we have the estimated state density or posterior state density. This quantity yk given xk, it's basically a model, probabilistic model of the sensor we are working with. And this is the state transition density. It is the model of the target motion. So a target can move with different models like constant velocity or nearly constant velocity or constant acceleration, or it can make some nonlinear motion like circular rotation. So now let us look at what happens. What are these quantities xk and yk in a realistic environment? So still I haven't defined really what target tracking is. So this is currently the textbook definition of Bayesian state estimation. It's a sub-area of control theory and signal processing. It's somewhere in between. For example, when you look at it from a control theory perspective, it is just the observer, theory of observers. Probably you have seen it in the basic control course before. And when you look at from the signal processing perspective, it is just a filter. It's a low-pass filter. Common filters that we are using are nothing but non-stationary low-pass filters. So, or time-varying low-pass filters. So here we have the target of interest. It is a car in this instant, and we need to have a model of how this car changes its position or its state variables. State variables here can be thought as position, velocity, acceleration, or as I said, it can be some discrete variables like type, color, I don't know, they are called as attribute information here. And we're observing this target state from a camera on a UAV, and this, in this case, yk is usually only a kinematic variable like position. Or if you have an image sensor, you can have the color or intensity, etc. And therefore, we would like to estimate xk by observing some observable variables here. So now, so this is the original textbook problem definition here, and what distinguishes this textbook definition or this well-known theory from target tracking? Let us talk about that. In this definition, I see there are more problems, but I see three immediate problems here. The first problem is, in general, f is not known. I don't know how a target moves exactly, and I don't know whether that dynamics changes in time or not. So F is a very basic problem of this textbook definition. If you don't know F, then you don't know those transition density, then therefore you have a problem. And in general, you don't know H, unfortunately. So, of course, if you have a single target and if you have a perfect sensor which really gives you information about the state, then you can know H. But no sensor is perfect. Sometimes sensor does not give you the measurement that you like. It can give you the measurement of another object in the vicinity. It can be another car, for example, in our earlier example. And sometimes so therefore there can be more measurements than you want to process. And there can be missing measurements as well. So image processing algorithm sometimes doesn't detect, or radar signal processing algorithm doesn't obtain its detection. So then you don't see the targets that you would like to observe. So therefore in general, this H has a very complicated structure, and you don't know it. And similarly, when you start tracking, the textbook problem definition assumes that the initial state has a known distribution. Okay? No one gives you the distribution of the initial state. You have to calculate it yourself. So therefore, these are the three immediate problems that one can talk about. So here is the explanation of the first problem with F here. So the target first moves with linear motion, and then it starts a circular motion here. So this is, therefore, if I put here into the filter, if I use the constant velocity or some linear state model, then I'm not going to be able to follow the target when it makes this circular motion here. This is called as the model mismatch problem in target tracking, and it is also called as the maneuvering target tracking problem. So when the model F you use in the filter for modeling the target motion does not match the actual target motion, then you have a maneuvering target tracking problem. So when we look at the other problem with H, we see that the sensor can get the measurements of the other objects, and no one tells you when you get a list of measurements in the sensor, no one tells you which measurement belongs to the target that you are actually following. So therefore here, you get a bunch of measurements and you don't know which one is the one that you like. So you can have more measurements than you need, and sometimes because of the image processing or radar signal processing algorithms, and because of low SNR, etc., you don't obtain the measurement of the target that you want. So therefore, these are the actual realistic considerations about H here. So therefore, we can make a target tracking definition here, which distinguishes it from the Bayesian state estimation problem. So I'm thinking about a target which is anything whose state is of interest to us. It's rather general here. And state we are interested in can change with time and with an unknown dynamic, so we don't know F. Measurement origins are uncertain, so we don't know which measurement is coming from which target. And there are false measurements, so spurious measurements that you don't actually want, and some measurements might be missing. Sometimes you don't detect the target. And in general, we don't have an initial guess or an estimate. So these quantities are making target tracking distinguished from the Bayesian state estimation problem. So therefore, target tracking is nothing but, in its most general and abstract form, is a realistic version of dynamic estimation theory. So it is the task of using dynamic estimation theory tools in a realistic environment. So in this presentation, in the rest of this presentation, we are going to consider these two problems. How are we going to handle the false measurements, and how are we going to handle the missing measurement cases? So I'm going to be working on a basic scenario, and we are going to go in increasing difficulty direction. So I'm going to first assume that probability of false alarm is equal to 0 and probability of detection is 1, and we are going to solve the estimation problem only. It's the Bayesian estimation problem. And then we are going to let the detection probability be smaller than 1, strictly smaller than 1, and we are going to handle missing measurement cases. And then we are going to increase false alarm probability larger than 0. So then we are going to also handle the spurious measurement cases. So here I'm assuming a single target which is present at all times. So I won't consider multiple target tracking problems, but in multiple target case, these problems be much worse. So it gets really bad when we have more than one target. So sampling time is 1 second, and we are considering a surveillance region of this size. and we have the state vector here, which is composed of xy positions and xy velocities. So we are assuming that our target goes with nearly constant velocity, right? So this means that I have here xk, which is related to the xk minus 1 with a single matrix A here, and I have some process noise representing acceleration here, which I don't know. So here, this is nothing but high school physics, because the position at time k is the position at time k minus 1 plus t times the velocity at time k minus 1 plus some unknown acceleration t times t squared over 2. So this is the model that the target is using. So in this presentation, we know the model that the target uses. So we are actually knowing what f is in this scenario. We are only considering uncertainties in h in this presentation. So here I assume that the unknown acceleration standard deviation is 3 meters per square. So therefore we have a distribution for the process noise here. Then, and I'm also assuming that the initial conditions, initial distribution of the target state is known. So therefore here, I'm actually getting rid of two problems. The problems with f and the problems with the initial state. Okay? So the only problems are left, which are left are the problems with h here. So if I use this model to generate some example trajectories, this is what I get. So the target starts around from origin here, and it goes in northeast direction like this. So this is what this target model can actually model. It is example scenarios that you can obtain with this state model. So here let us consider the simplest case. Probability of detection is 1 and probability of false alarm equals to 0. So therefore, probability of detection is 1, so therefore you always detect the target. You always get the measurement of the target that you like. And probability of false alarm equals to 0 means that there are no spurious measurement which doesn't belong to the target that you would like to follow. So here we are assuming that the sensor measures the position of the target. So we have the measurement equation given like this, and I assume here 20 meters standard deviation accuracy in the sensor. So whatever you measure, you add, a noise is added onto the true measurements that you get. So here what it looks like. This is an example scenario that I have. So this is the true target trajectory, and I have the measurements from this equation. This is a random trajectory measurements that I get. So therefore, the task of the tracker is just to follow the target from the start to the end. So let us summarize here the scenario. So in this case, we know here ABC matrices. So we have linear dynamics and we have Gaussian noises here. And we have a Gaussian initial state distribution. This case is called as the linear Gaussian case in estimation theory, and it's well known that in this case the problem can be analytically solved. So the posterior distribution we obtain can be analytically obtained, and it can be shown that all distributions that we would like to obtain here in this case are actually Gaussian. When everything is linear, when everything is Gaussian in the problem, then the problem is solved. And in that case, all of these distributions are Gaussian, and all we have to do is to calculate the mean and covariance of these distributions. So therefore here this density is going to be important. It is called the measurement prediction density. And let us now look at what happened in this case. In general, we have an infinite dimensional estimation problem. We need to obtain the posterior distribution. So you can think a distribution as an infinite dimensional vector, a continuum of numbers that you need to estimate. But here, in this case, I can represent a Gaussian density with a mean and covariance. Therefore here, in this specific case, that infinite dimensional problem turns into a finite dimensional problem for which you need to estimate only the means and covariance of the Gaussian distributions. So therefore, in this case, an infinite dimensional estimation problem reduces to a finite dimensional estimation problem. So instead of propagating distributions, you can then propagate the means and covariances of these distributions. So this is a finite parameterization of the distribution that you would like to obtain in this case. So therefore, you have the prediction step and the update step. And how you obtain actually these predicted means and covariances from the previous estimated means and covariances, and these ones from these are these propagation equations are called as the Kalman filter. Okay, so the rules for propagating means and covariances in this specific case are called in the literature as the Kalman filter. Okay, so a Kalman filter has a prediction update and time update. And in the prediction part, you only propagate time here. So here this notation means estimate of k given the measurements up to time k minus 1. And here is how you obtain the predicted estimate from the previous estimate and predicted covariance from the previous covariance. So here is the update version here. So you get the measurement inside your estimate, the current estimates here, and you have the covariance update given like this. So a very important property of a Kalman filter is that as every Bayesian estimation algorithm, it can predict the current measurement before actually it arrives. Okay? So from the previous information, I can predict with the Kalman filter what the new measurement is going to be. That is very critical. So and it also this difference is then called as the innovation quantity in the Kalman filter. So you subtract from the prediction of the measurement the actual measurement here. Okay? So that is called an innovation, and Kalman filter also tells you the covariance of that difference. So you know what the next measurement will be before it actually arrives, and you know the uncertainty around it, how much uncertainty you have. That is going to be very important. So the solution of this case, I can run the Kalman filter and obtain the red estimates here. So it just applies some form of optimal filter on the measurements, and I obtain just these red estimates. That is true target and I have red circles in both figures here, and crosses are measurements, and circles, blue circles are the true measurements. So it does a pretty good job of low pass filtering the measurements here. So now let us go into the second case, which is going to be the case when the probability of detection is actually smaller than 1. Meaning that I'm going to have some missing measurements in this case. So the measurement of the target that I would like doesn't arrive at some times from the sensor, whatever the reason is. It is in general the low SNR or a problem with the signal processing algorithm that you are working with. But I'm assuming false alarm probability is still 0, so we don't have spurious measurements in this case. I assume here detection probability is 0.8, so we are going to randomly erase some measurements from the list of measurements here. So when I erase those measurements, you see what happens here. So in the random run, I don't have some measurements in between the actual measurements here. So then what happens? I can actually summarize the solution for this case, again using the Kalman filter idea. So when you actually obtain a measurement, you know that it belongs to your target, and because you don't have any false alarms in this case. And when you get a measurement, you know that it's coming from the target that you would like to estimate. So here you can actually write a very basic Kalman filter which is suitable for probability of detection smaller than 1. The prediction update is the same, it's not related to the existence of the measurement. But the measurement update is conditional now. If you actually detect the target, if you get a measurement, you make the usual update of the Kalman filter. But if you actually do not detect the target, then this means that there is no new information in the sensor. That means that you need to equate your estimates to the predictions. So that is the only information that you have at the current time, because the measurement didn't come, so the sensor didn't provide any new info to us. So therefore I need to just equate the predicted covariance to the estimated covariance and estimate to the prediction. So that is the basic solution. So if no measurement comes, you just skip the measurement update part, and you just equate your means and covariance estimates to those of predictions. So here is what happens here. So I have these missing measurement cases, and in this case that is estimates when PD is equal to 1, and this is the case when PD is smaller than 1. So I'm going to switch them back so that you see which one is more noisy. So you see that the estimates when PD is equal to 0.8 are more noisy, which is expected because there is less information coming from the sensor. So therefore, Kalman filter just loses some of its information, but it's still fine to work with. So here we now come to the most difficult case for this age in the single target tracking case. So I have so in this case I have the PD smaller than 1. So I have sometimes I don't have my measurements, and I'm going to increase the probability of false alarm to a value more than 0. So now in this case I have just more measurements than I need, and sometimes I don't have the measurements that I want. So in this case these spurious measurements are called as clutter in tracking literature. And these are the definition is the non-persistent measurements which do not actually originate from the target are called clutter. Okay? So in this case I have to estimate my target in this environment. So okay, so everything so that is just I get a point cloud from the sensor, and in this picture I need to track my target. All right. So if you try to see the target here, it's rather difficult as you see when you look at this type of time picture. So now let us go into the solution. So we're going to present a solution in 2 steps for this most difficult problem. The solution has 2 steps. The first part is called as gating, and the second part is called as data association. As you see in this picture, most of the measurements that we collect actually are far away from the actual target. So these are called as outliers, and we can actually eliminate some of the measurements right away by using the predicted measurement of the Kalman filter. Right? So Kalman filter gives us actually a predicted measurement where the next measurement will be, and an uncertainty region about it with the density it calculates. So therefore I can get rid of some outliers right away. That is called as gating in target tracking. And although you get a measurement, although you can get rid of some extra measurements, sometimes there are still more than one measurement that you have to consider. And in that case the other problem, the other solution comes into the picture, which is called as association. So association is a way to handle multiple measurements that you get after gating. So gating is the process of using prior information or sufficient statistics. Sufficient statistics means what Kalman filter actually calculates to exclude the possibility of assigning a measurement to a target. So from the Kalman filter, you get a predicted measurement, and you get some and after you put the predicted measurement into measurement space, you can also draw a region around the predicted measurement, which would be an uncertainty region in which you can actually allow the assignment of a measurement to a target. So here, this is the predicted measurement, and that is the region that you draw inside the measurement space around the measurement. And if you can draw such a region, then you can always exclude the measurements coming outside this region. So that region is called actually as a gate of the target, and you discard all of the measurements outside the gate, and you use only the measurements inside the gate to process with your Kalman filter. So how do we do gating? So that is the predicted measurement, and I have the predicted covariance here, and I have the predicted measurement distribution here. So I can simply define a test here, statistical test, so that when I substitute the new coming measurement into this predicted density, which the Kalman filter calculates, it's a Gaussian. If this substitution gives me a number larger than a threshold, I accept the measurement, and if it is smaller than the threshold, then I will discard that measurement. So this test in the Gaussian distribution case is equivalent to that equation. So this is the statistics that we calculate. I put each measurement into yk here. I know sk and the predicted measurement here. And if it's smaller than the threshold, then I discard it. I accept the measurement. If it is larger than the threshold, I accept the measurement. I discard the measurement and do not use it. This is called as ellipsoidal gating in the Kalman filter, and of course we use some statistical or probabilistic ideas to actually calculate the gate threshold, gamma g here. So here I'm going to run a simple scenario. I will show the results of a simple scenario here, where I apply gating with the Kalman filter. I will show the gate using the red circle here. And what am I going to do, for example, when there are multiple measurements inside the gate? I'm going to, in this example, I'm going to just choose the closest one to the measurement. And I will just try to handle uncertainties in that manner. So now let us see. So here, everything in this one, we are going to see everything actually looks pretty good. With gating, I discard any measurement outside this gate, and I use only the measurements inside this gate to continue. So I discard all measurements around here from the Kalman filter. And when there are multiple measurements inside the gate, I accept the closest one to the predicted measurement. So here, but this does not work really good for some runs. And now I'm going to show you an example of that run. So for some time it really looks good, but after some time we see that the tracker actually loses all of the information about the target, and then it follows just some spurious measurements after that. So this is called as tracker divergence. So by adding the gate idea into the tracker, I actually obtain a feedback loop. So I tell the sensor, in some way, I tell the sensor to not look outside the gate. So in that case, as every feedback-related system, we can have an instability problem. Let us see here what happened at time 8. So here, for some time, some measurements do not arrive. So no measurements inside the gate. And at time 9 here, I don't get the measurement of the target here, the actual measurement of the target, but I get a spurious measurement here. Okay? Since I accept just the nearest measurement inside the gate as my tracking idea, the Kalman filter just accepts this as a measurement, and then this gate shifts to the right. In the next sampling instant, although there are measurements around the target, I don't see them because they're outside the gate. So then everything is finished. So you lost the target, and you will never recover from this situation. Actually, the result, this is actually caused by the gate size here. So this gate size is not really appropriate here, right? If I had a larger gate here, then I would get this measurement as well somehow, and maybe I could have continued tracking in that scenario. So I will show you that the reason is actually wrong modeling or being non-Bayesian. So here we come to the problem of data association, Data association is the way to actually handle multiple measurements inside the gate. And the most basic data association algorithm does this. Just choose the nearest measurement inside the gate. Just assign the nearest measurement. That is called as nearest neighbor data association. And it was an idea that was used for a very, very long time. And it causes actually problems. One of the problems with it is actually the scenario that I have shown you. So here we actually select the closest measurement to the target, and actually in the gate, and if gate does not include the actual target, then we have a problem. So therefore, non-Bayesian approaches actually might not be able to model the uncertainties well. So we are going to look at here the probabilistic data association algorithms. That is the Bayesian approach to the data association problem. In this case, we actually give or create some hypothesis about the measurements inside the gate. So the zeroth hypothesis, which is called as H0, tells us that no measurements inside the gate actually belongs to the target. And the other ith hypothesis tells us that the ith measurement belongs to the target. So if you have m measurements inside the gate, you have m plus one hypothesis about the origin of the measurements. So the first hypothesis says that none of these measurements belong to the target. The other one tells that one of the measurements, the ith one, is actually belonging to the target. So when you have these hypotheses, which are nothing but random variables, our posterior distribution becomes a mixture. So by basic probability rules called probability theorem, you can actually write such a formula. So in this case, our posterior distribution is actually a mixture. And for each hypothesis, I can actually calculate the specific posterior distribution depending on the measurement that I use. For the zeroth hypothesis, I need the updated measurement, the updated posterior distribution becomes the predicted posterior distribution because there is no measurement with the hypothesis. For the ith hypothesis, I need to use the ith measurement in my update. So these are given as the predicted estimate for the zeroth hypothesis and the updated predicted estimate for the ith hypothesis with the ith measurement. These are nothing but Kalman filter equations corresponding to each of these hypotheses. So therefore, for each hypothesis, I obtain an estimate and the covariance that would be resulting from each hypothesis assumption there. So therefore, if I have m measurements inside the gate, I calculate m plus 1 updated estimates and m plus 1 updated covariances. Then how am I going to use those means and covariances? I'm just going to merge them using the hypothesis probabilities. Okay? So I just use all of these hypothesis results and then I merge the results by using probabilities of those hypotheses. Okay? So therefore I have here some hypothesis probabilities, and what I do is actually to merge those means and covariances that from each hypothesis. I merge them using some probability rules here, and I obtain again a single mean and covariance to continue in the next time step with the Kalman filter. Of course, the general effect of this is actually to approximate a mixture with a single Gaussian. When I approximate a mixture with a single Gaussian, this generally results in a Gaussian with a large covariance. Okay? So that uncertainty increase when I have multiple measurements will be useful for us in solving the data association problem here. So therefore, this is our resulting algorithm. Prediction update is the same. I have nothing to change there. So because it's not related to the measurements. But in the measurement update, I do the following. I first gate the measurements. I take only the ones around inside my gate, which is around my predicted measurement position. I gate the measurements and I get a number of measurements left. So then I calculate these hypothesis probabilities. I generate hypotheses and then I calculate their probabilities. And for each hypothesis, I calculate also updated estimates, okay, and covariances of them. And then I merge them to obtain a single mean and single covariance to continue in the next sampling instant with the Kalman filter. So now I'm going to show you the first run that I have shown you before, and in this case we are going to see that everything is almost the same. So the green one shows the green circle shows the probabilistic data association, PDA estimate, and the covariance and the gate, and red one shows the nearest neighbor estimate that you have seen before. In this case, we don't have any changes. So both algorithms uses similar techniques in the good cases that I would say. So here you see that PDA gates, green ones, are slightly larger in this example. We're going to see that in the problematic case that we consider, these gates will be significantly larger due to uncertainty increase due to multiple measurements. Let us now see the problematic case. So at time 9, the problems appear. So this is usually what happens. So if I show you the problem part, so in this case, PDA can actually perfectly track the target, but you see that the gate changes its shape, and the important point is to see that the true target is always inside that gate. So at the problematic time here, the problematic measurement is inside the gates of both algorithms. But let us see what happens to the gate of the PDA after getting that measurement. So here you see that the nearest neighbor algorithm, because it didn't consider those two hypotheses that would appear in that case, its gate is small here. But the PDA gate is expanded to actually include the actual target here. And actually it gets both these two measurements with the spurious measurements in the next sampling instant. So in the next sampling instant, PDA gate is again larger and it contains a true target. The nearest neighbor already diverged here. And if I continue, some other spurious measurements make the PDA gate even larger. But after some point, when there is no spurious measurements, PDA gate starts to concentrate on the true target, and it continues in a well manner afterwards. So if I run these random scenarios 10,000 times, which is called as a Monte Carlo run here, these are the position and velocity estimation results of these two algorithms. So PDA is not perfect, of course. So here the blue curve shows an oracle algorithm, which is clairvoyant. It knows which measurement belongs to the target, and so therefore it's unrealistic, but it gives us a lower bound of performance here. So the best performance I can get is the blue curve. The red line shows the performance of the nearest neighbor algorithm, and green one is the performance of the PDA. So PDA is not perfect, of course. It misses in some runs also. So therefore, you see the increase in the position errors as time progresses. But it is much better than the non-Bayesian algorithm that we considered. So therefore, we come to the results. So here, what we have seen actually, modeling, making good modeling about the situations in target tracking actually makes the difference between Bayesian approaches and non-Bayesian approaches. If you do the probabilistic model nice in a Bayesian way, then you model the uncertainties in a good way, and that gives you the ability to handle more complicated cases than non-Bayesian approaches. So here, what did PDA do and what did nearest neighbor do? Nearest neighbor chose the best hypothesis at the current time. Okay, so actually you can think that the nearest neighbor was also a multiple hypothesis algorithm, but it chose the best hypothesis at the current time. It chose one of the hypotheses. But what did Bayesian algorithm do? It chose actually all of them. It used all of them and it merged it. Okay, so actually choosing one of the, sometimes in this type of situations, using all of the hypotheses and merging them is more useful than choosing the best hypothesis. So choosing the best hypothesis is a greedy idea. So you choose, you just think that this is going to be best for me for the current time, but in the next time step it might not be really good for you. So you choose all of them, you combine all of them, and you obtain a better thing in the long run. So this idea actually is used in, EDA actually is still used in real systems still today, and it has a multiple target version. It's called as joint probabilistic data association. And using all hypotheses instead of choosing one of them has many ideas. It also has ideas inside the maneuvering target tracking case. Instead of choosing a single model for the target, use multiple models for the target and try to combine them. That is also an idea that can be applicable for multiple maneuvering target tracking cases. So actually this concludes my presentation, and I will show you some references. So maybe we can also put the presentation online, I don't know, somewhere, so people can see these references. So these are called I can call them Bibles of target tracking. So the first one I use in my target tracking course that I gave a few years ago. And if you are new in this area, in estimation theory and target tracking, this is the book that you have to really study. So that is the most basic one, and it gives you all of the main ideas that are necessary for studying in target tracking. And there are of course some new books which are related, for example, to particle filters instead of Kalman filters. Particle filters are nothing but advanced forms of Kalman filters for non-linear systems. And also there are some ideas, very recent ideas, related to random sets, which are used in multiple target tracking. But that's all for now. Thank you very much.